except that the NGAPA is fast and easy to use. In this correlation here, the correlation is about 1-to-1. We did all different type of pie, H pie, concrete pie, stinger pie, Baker BPT, which is a kind of soil investigations tool, or the gas pie. And then the instant NGAPA. The I there stand for the instant. This is the instance compared to ICAP has a lot of advantages. The NGAPA is for any pie configurations, uniform, non-uniform, even pie with crack, with added damping. So what is added damping? Added damping, for example, when you have a pie template and the pie is rubbing on the template, so that is the template cause the skin friction, which is not part of the pie capacity. So that we can use that added damping there, and CAPWAP can do this. So is NGAPA and INGAPA, but ICAP does not, because ICAP is kind of limited. In ICAP, it is one-way export from ICAP to CAPWAP, but not vice versa. With instant NGAPA, it's two-way communications. INGAPA behave exactly the same as NGAPA. I'll show you later on. The results is plotted in real-time during driving. And the fourth module is GPC wave, which is similar to GIL whip. Again, whip will remain the gold standard. GPC wave was coded for driving criteria development. And as such, as you can see later on, it's much easier to use to develop driving criteria than whip. So some background here would be, this portion would be pretty fast. It's for people already familiar with dynamic load testing. So with whoever a beginner, they would need to research this. The shown here is the PDA gauges. So one strain gauge and one accelerometer is on one side of the pie, and strain is measured. So the force is correlated, directly calculated using this formula. And force is proportional to the square of wave speed. ZV, Z is impedance, is proportional to wave speed. So when you divide F by ZV, you would have F divided by ZV is proportional to wave speed. So when you change wave speed, you would change the proportionality. So let's take a look at one example. I haven't opened the program yet. So the program has, this program has three main modules here: GPC review, NGAPA, and GPC wave. Let's take a look at one example. And it would be this. So this concrete pie is not, this type of concrete pie is not allowed in FDOT yet. This is cylinder centrifuge concrete pie, which the wall is pretty thin. In this case, the wall of this one is only 7 inches. A Malaysian company introduced this to FDOT about, I would think, 10, 15 years ago, and FDOT rejected the, this kind of pie because the lateral, mainly because of the lateral capacity, which some crack, something like that. So this one, the strength, this type of pie, the strength is extremely high. As such, the wave speed is really high. Wave speed for this kind of concrete is really high. This type pie is very popular in South Korea, in Japan, and in all of Asia. The strength at 28 days is typically 100 megapascal. What was that in KSI? Let's see. Pressure megapascal 100 and going to KSI. So 7,200. Is that? Oh, this is TSI. So KSI would be, so it would be 14.5 KSI. So it's extremely high strength. As such, the wave speed is high. Let's see if this wave speed is reasonable. So in this pi, 2 here is a 2L over C marker, which is the inner pi. Tau is not clear. Let me turn off displacement. Smile a little bit. So a 2, the tau is not clear, so there's no way to tell what is the right wave speed for this pi. Also in Asia, they usually jack pi, not dry pi. So they jack pi like 90% of time, and only do the test, the restrike test for 2 or 3 blows. So tau is not clear, and because of this, wave speed has to be judged based on the concrete strength and based on the proportionality. So if I reduce the wave speed here, the wave speed is 15,750. If I reduce it, let's see, if I reduce it, it will change the proportionality. So it's now not proportional when I use a low wave speed. So wave speed will change the proportionality. And in the GPC and NGAPA packages, it's very convenient to change the number by just click on that digit and scroll the. I'm not sure if the camera is on, but scroll this wheel here on the mouse. So back here, this is example to calculate wave speed from concrete strength. Wave down is property of the hammer. So wave down represents the hammer input. Wave up represents soil resistance. So in all the documents that we've seen in the past, long time ago, they usually talk about F and ZV. Nowadays, when I present, I tend to present more about wave up instead of F and ZV. But those two are related. So when the pi has soil resistance, skin frictions, for example, F and ZV will separate from each other. So that means wave up will increase. That's very simple. So when you have soil resistance, you will see wave up increase. This is the second part of the background regarding displacement. So displacement is integrations of velocity. Velocity is integrations of acceleration. So displacement would be the double integrations of acceleration. dmx is the maximum displacement, and it occurs around 10 to 20 milliseconds. dfn is the final displacement, which is around 100 to 200 milliseconds. Now, assume acceleration error of 0.1 g, which is 1 meter per square second, or this. Then you can calculate what is the error in dmx. So double integration for 10 milliseconds here, you have almost no error. So dmx is very reliable, whereas dfn is not. When you double integrate to 100, this is 100 millisecond, 0.1 second, which is 100 millisecond, you may have this much of error. That's a lot. So because of that, sometimes DFN is totally wrong. I give two examples here. One example, you have negative DFN, and the other example where DFN is not stable. And this happened to any systems, PDA, GPC. A lot of time it looks stable, it looks good, but once in a while you will have this issue here. And because of that, there's a need to adjust the end of accelerator records. And this is a CAPWAP example, but N-GAPA adjustment would be similar. I will show you later. The third part of the background is regarding hammer type. This is relating to the data mostly. So diesel hammer always have gas pre-compression before the explosion of the diesel. So it has force prior to impact. So in soft drive, this the first graph is soft drive. The second graph is into some soil resistance. So for both of these graphs, the force, the pre-ignition force is about 40 kPa. So here 40 kPa here, and down here is also about 40 kPa. But when it's soft driving, that portion is pretty high compared to the maximum. So in this in the soft drive, that 40 kPa is about 1/3 of the mark, whereas this is almost nothing, almost zero. Now, for air or hydraulic hammer or drop hammer, the force would be zero prior to impact. So that will affect the some of the evaluation of the record. So what happens if F is more than zero before impact? So when the pi is being driven without much resistance, that means easy driving, we know that the wave up, the red one here is the wave up, is a mirror of the wave down, but 2L over C later on. So with the hammer, without forces prior to impact, this is, for example, drop hammer, hydraulic hammer, air hammer, you have this. With diesel hammer, you have that pre-ignition force, and that mirror there is because of the end of the pi and the pi impedance change. So there's tension reflection at the toe of the pi when the impedance stop. So you have the mirror there, and this wave sloping down will cause the program to sometimes misinterpret and show a beta, even though the pi is good. Let me show example, which is here pi 6.2. Open pi 6.2 here. So this is the example related to that. Easy driving, you have this wave up is a mirror of the wave down. See after that, and because of that, it's sloping down, and that is normal. Now in this program, to change the scale, you can click anywhere. You can drag, but much easier to just click. So click like this is to change the scale, or you can drag. And to go to the next blow, you can do this, or you can just scroll the mouse on the wheel here. So when you scroll the mouse, that go to the next blow. Another way is to use the arrow key. So you use the arrow down or arrow up key. Now I'm pressing the arrow down. That's going down toward for this graph, or the paste down. Same thing. I'm pressing the paste down. It's going toward downward the graph there. So while I'm on this screen, I wanted to show you this graph to present this in a smoother way. You can change this filter. So this filter here is only for the graph. So 1, 2, for example, 2. So average 2, that's make the average every 2 point. So that's the curve here is smooth. So the filter here is for the vertical graph. The filter down here is for the data. I'll show you later. So filter here is for the data. Filter here is for the graph. Now, generation ago, the previous engineer taught the next generation of engineer that FVP, the proportionality means FVP close to 1. I was taught that way, and I practiced that way for quite a long time before I realized that it's not quite right. The PDA manual here, as I mentioned here, PDA mentioned PDA clearly say that the proportionality here means that it's smooth to the impact zone. It does not mean FVP is 1. It does not mean that. But generations taught the next generations that proportionality means FVP is 1. That is not totally true, not totally right. It only true for one particular case. It's only true when it is non-diesel hammer and there's no skin friction within the rise time. So this is very rare though, to have this. You have to be non-diesel hammer and no skin frictions occur before the rise. So proportional only means that the wave up is smooth through the impact zone. And this is, I presented earlier, when the hammer has a pre-ignition force, the easy drive, it will cause wave up to go down, and this proportionality here in this case, FVP here is less than 1, much less than 1 in this, and it's okay. The opposite example is when you have skin frictions near the sensor. So when you have skin friction near the sensor, at the distance, in this example, distance of A, then at the time 2A over C, you have that skin friction reflection. So that skin friction reflection there would cause the wave up to rise up. And obviously at the peak there are a lot of skin friction already. And that's, in this example, the FVP would be higher than 1. So the conclusion is, if wave speed is correct, and if signal matching, either CAPWAP or NGAPA, can simulate the wave up reasonably, then any FVP is okay. But one of the important thing is you have to make sure that the wave speed is correct. And generally, there's no need to change the replay factor. When the hammer has smooth force rise, in this case, diesel hammer, very smooth force rise, couple of soil resistance, sometimes it makes it very difficult to detect the pie-toe deflection. And this, you can still see the pie-toe reflection, but in some other case, it's almost a straight line. And there it's very difficult to evaluate where is the toe. Now, I'm going to give you some example. Oh, I forgot the key. That's okay. I can, the PDA key. I can go to the end my remote machine. So I'm going to open a few examples where the program, the PDA program, would pick up T0 differently because the force rise is too smooth. So let's keep this example first, and at the same time, I'm going to present the NGAPA as well. So in this example, the T0 was picked up a little bit late. As such, the toe is being detected late, and let's show beta. Beta. So the program would show beta of 72% because the 2L over C marker is a little bit too late because the T0 is late. Let me copy this. So from here to NGAPA, you just copy to clipboard. Is copy to clipboard, or use the Control C. So I copy that to clipboard. I paste to Notepad. I paste this to Notepad. I save this. Save as in document, and I save this as example 1. Save, and I'm going back to this module here. Close this. Open NGAPA, and I'm going to open that file. So right now is open NGAPA, showing all file, and when I'm opening this, it will, you can hit either OK or cancel. If you don't adjust, so if you don't adjust the accelerometer record, you can hit either OK or cancel, doesn't matter. It will show the in-GAPA result. So what it just did, that's the in-GAPA, instant signal matching. So in this, it picked the T0 around the right time, and is in this instant match here, it showed the pi 21 kips and beta 89%. So the beta here 89% is different than PDA because of the T0 mark. So T0 pick up the right point and tau was the right point, and therefore the 89 is because of the sloping here. But so here that's the instant n-GAPA results. Let's go take another example. Close this file. Open next file. Okay, this one. So this one here, the hammer, the rise of the hammer is too smooth. It couldn't detect the right T0. So the same thing, because of that, the tau was detected incorrectly, and it showed beta 88% here. You can try different impact point method. So in this, you can try different impact points. It doesn't help much here. Still the same result. So let's copy this. Copy to clipboard. Paste it to Notepad. Notepad. Save as example 2. Save. Go back to here. Open. I don't necessarily need to save this n-GAPA file. So I just choose this and all file example 2. Okay, and for a moment it will show the instant n-GAPA results. So that's the instant n-GAPA results there. Mask quality is almost near perfect. The beta here is 97%. So here it detects the T0 more accurately, and as such, the beta is more reliable. And beta here will not be rounded. In PDA, whenever beta is more than 90%, it will round to 100%. In GPC, it will never round. So it will show 90-something percent. PDA, if it's more than 90, it will round to 100. So WaveUp is really important. We can see all kinds of different things based on WaveUp. Example here, almost no skin frictions. The lower one here, almost no skin friction, almost no end bearing. So the rise of the WaveUp after 3 hours over C represents end bearing. So in this red one here, that's good end bearing. That's very good end bearing, and the magnitude here would sometimes represent the quake, the toe quake, if the force transfer to the toe. So if for some really large deep pi, if the hammer is too small, one of the examples that I showed earlier, the centrifugal pi. That pi, the force did not transfer much to the toe. That's why you don't see. Let's go back there. Let's go back to this centrifuge pi. Oh, I'm sorry, not in the slide. I presented live. That one, the force did not transfer much to the toe, and because of that, the toe is undetectable. And in that case, you would not be able to evaluate the toe quake based on the tensor reflection here. So here it means the last tensor reflection here, last in white here means toe quake is last. In this case means toe quake is small. The reflection here represent the reflection of the splice. So with this kind of reflection, is the splice good or bad? It depends. So for mechanical splice, if you monitor from the beginning to the ends, and if the reflections always stay about the same, or maybe a little bit more maybe a little less, most of the time, the mechanical splice is good. But if this is for epoxy splice, then this splice is failing on epoxy splice. If you see something like this on epoxy, that means this splice is failing. On this one, it has very good skin friction because wave up, slope up dramatically, and then sloping down gradually. This sloping down is the unloading skin friction, or negative skin friction. In this case is unloading scenario, and when that happens, the program may misinterpret and will show incorrect beta. Why you have unloading skin frictions results or negative skin friction in this? So relate to this static load test. So whoever done static load test with instrumentation before, it will be easier to understand. So in around 2004, I was with Langen, and that was the first time I did static load test with instrumentation. Before that, I did static load test before, but I was not. We did not do instrumentation, and because of that, I did not learn about the unloading. And when I did the static load test with instrumentation, I realized, oh, wow, the soil really locked in the stress. So this is the loading stages. And when you load, you have skin friction develop like this. When you unload, so we remove the dead load, remove the load from the jack. And when the load is zero, the stress still lock in the soils, and that causes the negative skin friction in this portion. So, so this negative skin friction is good negative skin friction, not the bad down drag in the embankment surcharge case. So you need to differentiate that this is not the down drag in embankment surcharge case. Now in static load test, this unloading happened a few hours or even a few days after the loading. In dynamic load test, the unloading happened only a few milliseconds after the loading. When the hammer is still on the pie, a few milliseconds after, the unloading already happened. So you have negative skin friction of the unloading phase of the upper portion of the pie, of a long pie, arrive to the sensor at the same time as the positive skin friction of the deeper portion of the pie. So because of that, you have these unloading skin frictions. This unloading skin friction, even though it appears in a later portion, but it due to the skin friction in the top of the pie. So let's show example here. Example. Oh, we need to close the program. So an auger gas pie very deep, very long, 145, 147 feet, 0.9 meters diameter, which is, let's see, for some reason my ear is ringing. Open. So this one has incredible unloading. So the toe is here. In this example, T0 is picked up correctly. So T0 is right, toe is here, but incredible unloading. And PDA will show a beta of 0 because of that unloading. But the pi is good, perfect. So let's copy this, Control C, and then paste to Notepad. Save this as example 3. Go to the program, open, no need to save this. Or example 3, okay. Longer pies, it would take a little bit more time to evaluate, but should be done really quick. And this is the instant signal match results. More than 2,000 capes of resistance. The hammer is a little bit too small for this, and beta is the 100%. Evaluated by NGAPA. So this is the example where it has incredible unloading. How to validate that the downward slope of wave up is due to negative skin friction, not due to damage. So, so in order to have a negative skin friction, you would need to have negative velocity prior to the valley line. So back here in this program, the valley is here. This the second solid line. That's the valley, and the velocity is way negative before that. Velocity negative before the valley. So in NGAPA, it doesn't show the valley in NGAPA, but in GPC, if you open GPC, it will show the valley. So if you open GPC, I don't have that pi in GPC, but if you open any GPC file, it will show the valley here. In the beginning of the drive, valley would be matching with the lowest point on the wave up, or only on easy drive, and eventually later on, it will not match anymore. It will not match anymore, but it will still mark this as a valley, which is 2L/C after FMX. So this red line here is 2L/C after this. So when the pi has resistance, the lowest point here would not match with this anymore. I think this is fifth topic in the background. Case method. Case method results is the total resistance minus the damping force, and the damping force here is closely related to the velocity of the toe of the pi. So let me show you example here. If it was really small hammer, handheld hammer, you strike on the top of the pi, because the hammer is too small, so it never move. in my extreme example here, a pit hammer, all the pie wouldn't move, not necessarily a toe. And because of that, the damping force would be zero, because toe never move. So the damping force is zero, and the resistance would be the force that put in by the hammer. So in that case, JC would be zero. And because of this, JC is primarily a function of the hammer energy relative to the pi source system. And after that, this table is secondary. This table here is secondary. So example, drill shaft or last auger cast pi, you frequently see this low JC because the hammer it doesn't have enough energy to move the pi. For small, short steel pi, especially H pi, because H pi is usually very small, the toe moves much more, and because of that, damping, the lump damping JC is pretty very, very large, much more outside the range here. So summary here, the case method is preliminary, and it's not a gold standard, and it's stated so in many documents. This is 2016 versions of the driven pi foundation. It say that the signal match is much more accurate than the case method results. In the earlier version, it say the same thing. In early versions, which is 2006, it say the same thing, but it say CAPWAP here. In the later version, it used the generic term instead of the trademark term. In ICAP manual, it says that the ICAP is currently only applicable to uniform pi, while not as powerful and as accurate as CAPWAP. ICAP is still better than the case method, and expected to gradually replace the case method. In this 2012 stress weight paper, it says that the ICAP solution is more reliable than case method. So summary, case method is not a gold standard. It's a good reference, but not to be trusted. So that is the first part of my presentation. If you have any questions, Kelly, do you have any questions? Any question here?
I kind of answered it, but effectively, I see you grabbing PDA data, grabbing the text, and pulling it into your technology, so you can essentially evaluate PDA in yours.
Yeah, and it's pretty fast. Mike, one of the comment here, in GAPA, it's good to talk about this. In GAPA, one of the question is, would it be unique? The answer is no. It will change with the technology. So right now, the NGAPA is performed depending on the computer speed. We want it to be adapting to the computer speed. So with the increasing computer speed, we would be able to put more detailed analysis in the future, and would it be more accurate in the future. So it would not a unique answer. It may change 1%, less than 1%. Same thing with ICAP though. Some people thought that ICAP would be unique. It would be unique only for that version. When they keep changing, the ICAP results may change. So it Unix for a certain versions. The result of the ICAP in GAPA right now is very closely matching with the manual GAPA. And when we change, it might change small percentage of the results.
One question. I'm sure you covered this before we got here, but what is it that's enabling NGAPA to pick T0 better than that?
Just our algorithm. I don't know. It's not that difficult though. It's not that difficult to implement. I don't know why the PDA would have that difficulty sometimes. But we don't have problems picking T0. PDA once in a while, as some practitioner in here know, that once in a while it will pick the wrong T0.
GPC also pick wave speed automatically in the future.
Yes, GPC does evaluate wave speed automatically. Yes, I will show later on. Okay. So what time is it now? I don't have time.
10:20.
Quite early. So let's have just, oh, not actually I'm 5 minutes late. Okay, let's have a 2-minute break, 2-3 minute break, and then we resume with GPC acquisition. We have some anytime during the drive without any need to make a new file. So going to, okay, let me close this, no need for this, close that. Let me call GPC acquisition here. So in GPC acquisitions, you have to make sure that you connect to the same box. So this box is 1003, and on the Wi-Fi, I'm connected to GPC 1003. So you just make sure that you are on the same box. Now, for example, if I have the wrong box, it will not able to connect. Will not be able to connect, and it will say it will show message here. Turn off, turn on Wi-Fi, something like that. But yeah, disconnect and reconnect internet. But this is because of the reason is because of the wrong box. So let me go here, change the right box. So there will be two with the 1003. Whichever one is fine, with the same. So you can pick either one of these 1003. And when you change the pi length, let's watch. When I change the pi length, it will change the post trigger length automatically. So when I change this, it will change the post trigger length automatically. So what is post trigger length? The post trigger length is the length of the durations that it captured the record after it detect the hammer. You can change this anytime manually though. The program selects some number here by default for you, but you can change it manually. Why you need to change this? So let's use an example here. So during the drive, you will see if you have very long trigger length, for example, then this portion would be 0 for a long time. You don't need to capture that long 0. If it's all 0, you don't need to capture that long 0. You can reduce that number to reduce the file size. So this is related to the file size. But if you don't worry about file size and you just leave a big number there, that doesn't matter. So the so here as I mentioned, you can change this anytime during the drive. For PDA, you have to pre-select either 204 millisecond or 102 millisecond. It's a fixed number, and it's only in the before you drive. Once you drive, you'll not be able to change it. And if you have two file, one with 102 millisecond and the other file with 204 millisecond, PDA file would not allow you to merge the two files. But here, one file can have flows with all different kind of length. You can merge, if you happen to have two file on one file, you can merge it, no problem. So merging the file with different trigger with no problem. Same thing with sampling rate. One file can have multiple sampling rate. So let's go here. When you click here, it will connect to the box, and I'll show you. You can see me on this on the camera. So here is the two gauges. It's combo. Each gauge has a strain gauge and accelerometer within this. And one of the way to test how accurate the calibrations roughly is. Let me see which is. This is one. This is one. When I put like this, the acceleration, the static the number there is minus 2.7. So that's the 0 point. If I flip it upside down, it will be different by 2. So so let me flip it upside down. That's minus 0.6, and when I flip up is 2.6. So that's roughly about 2G. So the difference is about 2G, the static between up and down. Now, well, so one of the thing here is very, very nice about this is you can detect problem with sensors based on this graph, based on the graph here, without just looking at the, if you have only the option to see this number, sometimes you don't detect it. So let me put a bad gauge on and show you what bad gauge is. Let me unplug. So this is example where it's the graph is blind and it showed red here. So that is example. For example, during the drive, your cable is being cut. I have a bad sensor here, which 51133. So 51133, bad one. So this one, let's put it stay still here, and let's see. So, so right now it's 0, 0. It looks good, but let me. It actually this one has some cable issue. It's good now, but that's cable issue. Sometime it will. It looks good now, but it would have cable issue though. It will look good right now, but. Oh, it doesn't trigger actually. Let me turn off the app here, and then only tap. So it did not trigger. So see, it did not trigger the V. So this one is bad. Sometimes it even seems noisy though. Somehow today I did not see noisy, but this is a bad sensor. When I trigger this, the V doesn't show up. V doesn't show up here. Even though it looks perfect, 0 here, 0 offset there. Let me do the slow graph. So when you do the slow graph, the graph stay longer on the screen. So I'm going to tap on both, and then I'm going to turn on tab here. So when I tap on both, that's the results that you see on the screen. Let me show you a different one then. I thought this one, the bad one here would show noisy, some noise, but it did not. Let me change this to a different one. I put on the 4127 one here, and this number would keep changing. This number here would keep changing. The number here, the acceleration here, it keeps changing. It changes, even though it looks fast here, but it changes slow enough within 100 milliseconds, which is the durations of the blow time. That if you use this, so if you happen to use this, it may still give you good results. So let me do this. So actual drive here, change to V1, V2. So it may still give you good results because the duration is short enough that it's the graph here. The graph here, you can change it to automatic by right click here. That's the automatic scale. So the sensor may still give you good results. Sometimes it gives you noise, but let's go back to the sensor check. So this sensor, this V2 sensor here, the number is not stable, and that this number is not quite good, and that is the one that may give you the error in the small error with regard to the DFN. So let me go back to the slide. So DFN is accumulations of the double integrations to the end of the record, and it may give you a larger error of DFN. Let me unplug this. Okay, group one back in.
I want to put on what you're talking about. So is your post trigger time, is that where we define the DT for that integral? What do you mean by it takes the integral to the end of the record? Where's the end of the record? Is that what we're defining with the post trigger?
No, that's right. The post trigger length, yes. Yeah. So here, 51134, going back here. So now let me demonstrate the Wi-Fi to see what's the range it can take. And I may need I may not. Let me go walk toward the kitchens and tap this at the same time. So right now, the Wi-Fi, the signal of the Wi-Fi here, it's signified by the ready button here. So when it's flashing red, if it's flashing red, that means the Wi-Fi is too weak. So let me walk if it's flashing red there, it may be, that means the Wi-Fi is a little bit too weak. So let me walk with the kitchen and tapping at the same time. Let me see what blow number now. 26. Let me walk and count at the same time. 27.
What is the rule number?
31.
31. 2, 3, 4, 5, 6, 7, 8.
Oh, that's good. It's pretty good. That's pretty good.
Flashing red anytime?
No, no.
So when it's flashing red, that means the Wi-Fi is too weak. But even if it's flashing red, the box still collect data.
So even it's flashing red, it will transmit data as soon as it green again. So it will always collect data, even though it's flashing red. It will stop collecting data only if it stays red. If it stays red, then it will stop collecting data. Now this box is the version 3, actually, version 3. That box is version 2. That box is version 2 have weaker Wi-Fi. And with that box version 2 there, weaker Wi-Fi there, it will flashing red more often. Let me try that one. Let me try that box. So let's turn up that one on. And I'm going to connect to that box, which is box 1001.
So while you're doing this, are you able to maintain a drive log? Like you're still collecting data off of that, or do you have to start a new file when you're playing with your stuff?
What do you mean?
Will you come back and you'll still be collecting data in that same file, or do you have to create a new file and then go back and merge stuff?
No.
If you're troubleshooting in the field and you're having.
No, I can keep doing this. Yes, I don't need to make new file. So I'm waiting for the box 1 to come out. So box 1, connect to box 1, change this to box 1, and this one is the earlier version 2. Version 1 is the Dr. Goebel, Professor Goebel's version. So we have improved this quite a lot. Version 1 is Dr. Goebel versions, which we no longer use. Let's see. Okay, let's change this. And this, since this box was used by a different computer earlier, now it will say that, hey, this box was used by a different computer. Let's repoint this to this computer. So it will take a while in the beginning because it needs to repoint to this computer. So here, box previous used by another computer, now redirected to this computer. So we connect. So let me demonstrate this Wi-Fi of this box. It'll be a little bit weaker. So it will flash in red. This one would flash red earlier, 47, 48.
He did flash red now? No? Oh, that's good. It's still good though. You can't really play. That's good. This box is like it wasn't two. He will flash red more often than wasn't three. This one is good. Yeah, so Minggu went to our job site about 2-3 weeks ago, and he was really impressed with the way we collected the data. Nothing missed, and so it's very intuitive. And last year, I landed this to my good friends in Central Florida, and his finger is too big fat. At the time, the button is really small. He could not hit the button. So the screen here is touch screen. Here is touch screen, and he could not. So he could not touch the buttons, and after I visited his house, he showed me, hey, I could not touch that button. I realized that I improved that. So we've been given this for other firms to test, and we like, oh yeah, the button is way too small. So now just touch, it will change the graph here. So instead of selecting, earlier version I have to select items. Now just touch, it will change the graph. Let me change this. You wouldn't be able to see here though, but same thing would be here. Just click, click instead of selecting the option. So this tablet here is the touch screen ones, very convenient. Let's see what I need to say here. So during the drive, you can go back to the previous blow by the same thing. Use the mouse here, scroll up or down, or use the keyboard, or just click on the graph. So if you click on the graph there, it will go to that blow. You go to that blow. During the drive, the instant GAPA is going to do the signal matching automatically. And let me demonstrate. Let me end this drive, and I'm going to pull up a simulation, which is actual data here. So going to go to here, select simulate, and right now the match is coarse match. So we have the 3 level here: coarse, medium, fine. So this is the in-GAPA level. So coarse means it will be quickest, but it's rough. So if you typically select this for a long drive. For a long drive. For set check, you can select medium or fine. The reason is when you select either medium or fine, the computer may not have enough time to calculate between blows. So between blows, you have only less than 1 second to calculate. And if you select fine, it may take, for example, 2 seconds. And it will have a delay showing on the screen. But if you do a set check, for example, set check only 6 to 10 blows, it will show, it will have a delay on the screen, but because you end the set check only at 6 or 8, it will eventually catch up. The program will eventually catch up and show everything on the screen. Now for a long drive, 100,000 blows you don't want, with the current computer speed, you don't want to select fine, because it will accumulate the delay on showing on the screen. It will collect everything. It will collect everything. It will just delay on showing the screen. So if you choose fine math, it will have cumulative delay of showing the results. So let me show coarse math for now. And this simulation, the pi is 50 feet long. Let's change it to concrete pi here. And let's see. Okay, it looks good now. Earlier, for some reason, it's a little bit corrupted. So let me pause it for now. So first blow, the match quality is 6.86, which is not good. Earlier, when I mentioned it has bug because the stress were not right. Stress is okay now. So as you go, the match quality would eventually better. The reason is the second blows will use the results of the previous blow, and if you keep going, the next blows will use the results of the previous blow. So match quality here 2.55. But again, let me pause it. Again, the first blow, it's when you use coarse, the first blow, the match quality would not be that great. Now let me close, and I'm going to redo this using the fine match. So the fine match will take a little bit more time. So fine match, simulate. It would take a little bit more time. So it's doing now. So the second blow is not that good, but yeah. So the third blow and fourth blow, the match quality is now much better than earlier. That is because I use the fine match. So again, if you do a set check, you select, it's okay to use fine match, but for continuous drive, use coarse match. And I keep running now. So when I use coarse match now, though, match quality is still pretty good. The reason is it used the result of the previous blow. It used the match of the previous blow and keep improving on that. So it used the previous results and run the next blow using the results that is previously run. That's why the match quality is pretty good here. If so, the two curve here, one is from signal match, the NGAPA here, and the other is case method. Now you can change the case method anytime. Here, obviously, I use this for still project. This file earlier use still. So let me change this. And when I change it, the graph during the drive, the graph does not update it yet, though. This is acquisition only. Acquisition because it's depending on the data collection. So in order to update, you have to click on reanalyze drive. It will update. This one actually, the case method is not quite that sensitive. Now for GPC review, you don't need to click. There's no option for reanalyze. Earlier, the audience asked if GPC can pick up the voice speed. Yes. So during the drive, if it has good reflection, you can click this, and it would auto detect the voice speed to match the toe reflection. So now the voice speed detected by the program is where is it? 13,158 here, the overall voice speed, and it will change the top voice speed as well. So let me, for example, if I change this manually to different number to very high number here. Here. So when I change the top speed, it will have two lines. One line where the black line is for the line, the 2 LOC line based on that wave speed. It's on the pi top wave speed. And the blue line is based on the overall wave speed. So I haven't changed my overall wave speed yet. But if I match this, there will be only one line. So number here is 14258. Let me change this. 14258. All blows. So when I do that, there's only one line. Now, so in the beginning of the pi, you don't know the wave speed. You assume some number, and as you drive, let me resume driving. So as you drive, right now is keep driving. You can click this button, and it. So I just click that button, didn't drive. It's automatically pick the right wave speed for you. It have not updated the graph from 1 to 15 though. If you want to update from 1 to 15, you need to click on reanalyze drive. The priority for the program now is going forward, going for the next blow, not the existing blow. So you would want to do that when you have standby time, downtime. For example, right now the hammer has a pause, for example. Now you have downtime, and you click that, it will reanalyze the whole drive. LP, let me resume driving. LP, you can click this to increase the LP. What is the auto LP? So Jordan Nelson from our firm is, let me click this when I'm talking. Jordan Nelson from our firm is working on automatic device to record the LP automatically. So right now that number on the screen doesn't mean anything yet, but eventually we will have a device on the pi that pick up the LP automatically. That way the pi driving log would much easier. And if you, similar to PDA, if you miss it, you can revise this. For example, if you click too fast, you want to make this 4, you change it back to 4. So actually in this simulations, it's let me change, let me end this. If simulation, it doesn't work that way. Let me go to run, and right now I'm using that box over there. So whenever I change the sensor or change the box, the sensor balance will automatically comes up. And let me use that box. This LP. So if I go back here and tap, so yes, the program update the I think that's the different aspect of the question, I think. So let me answer next. But when I do this, one of the V automatically turn off. So the program, when the program see the 2 V are very different, it will already turn off one of the V for the user. All right. So, and let me try to see if I have, yeah. So when I tap it, eventually it will have a similar V, and when it has similar V, it will turn on the V automatically for you. So in GPC, most of the time, you don't have to manually turn off a bad gauge. The program do it for you. So if you have a bad accelerometer, the program will see right now one of the V is bad. It will turn off for you. So this is one of the distinguished feature here. The same with the force. Actually, the force, it will not turn off for you though, because it's required to have two forces. It's required to have two forces. It will not turn off the forces for you, but it will display, if it's really loose, it will display that sensor is loose. So let me open GPC review example where it has loose case. So the message, this is GPC review. The message of GPC review, let me see loose case example. Yeah. So let's see. Let's see which one is loose. Oh, here. So the user turn off. Let me turn on. So when the user turn off one of the F, it will exclude the analysis. It would not analyze that blow. So the program will already turn off that blow. So that blow will not be analyzed when it has only one F. Now when I turn on 2F, I have to manually click this button to include it. So it will detect that the F here, F1 is loose. It say here F1 loose. So let me do it again. If I turn off one, it will already turn off that blow. It will not analyze that blow. I would not be able to turn it back on. So it will stay excluded. It will stay excluded. If I turn on both F, it will allows me to include or exclude manually. But it will show the message here that the F1 is loose, really bad. So same with GPC. If it see one of the F is loose, it will display the message here that which F is loose. Now back to the questions for concrete pile driving in Pinnacle limestone. There is situations where the toe of the pile is walking away on the sloping rock and causing a crack in somewhere along the pile. That kind of damage is not because of the TSX, the average tensile stress. It's because of the stress on one side of the pile, tensile stress on one side of the pile, which will not be measured because TSX is average across the cross-sectional area of the pile. So that kind of damage, that kind of crack along the pile because of the toe is walking away, will cause the wave speed to be slower over time. So if the WC in that case will be degraded over time, and if you can turn on that features by turning off this button. So if you think that you were driving into Pinnacle limestone, you turn off this option, then during the drive, the program will keep changing the WC to match the new toe. And when it does that, eventually it will show a message here that the WC is too low. So it will compare that number to the WS, And if the WC is too low, it will show a message here. Hey, WC is too low. In that case, it means that the crack is kind of severe. Toe may be still quite visible, but the crack may be severe that the waste speed, the overall waste speed is now in dangerous situation, too low compared to WS. Let's see what else. Time shift. I have to go back. So let me do simulation again to demonstrate time shift. So resume driving, and if F and V have some phase shift, you can do time shift to shift the velocity. So during the drive, this is during the drive, right? You can turn on and off displacement. It's up to you. So sometimes I turn off displacement graph, easier to see the wave up. So during the drive like this, when you click time shift, it's only a number. So it's only a number. So for example, if I shift, let me shift extremely here. Let me shift 3 point. It will shift record it will shift V 3 point to the right. That's so you have a mismatch here. I use an extreme number here to show the extreme. But so during the drive, the time shift is just a number. But if you have a pause, for example, you have a pause during the drive, then same button there is graphical visual. So you can visually see what is the best time shift for this for the blow. So so if you have a standby time, this is the best way though. So for example, in this case, the most suitable time shift may be -1 or 0 if you want to keep 0. Zero is the wave is kind of curving a little bit up. So in this it may be about -1. Or you can type directly there. So that's time shift. This applies to GPC review as well. GPC review, of course, GPC review is it always have visual thing for you to select the time shift. Earlier the waste speed. How come it's now like this? Let me go back to this and detect the waste speed. That's time shift. Filter point for this data where there's no noise, no the gauges are pretty good like this. There's no need to use filter point. But filter point here is similar to PDA from 1 to 6. Oh, note. Very convenient note. So let me resume the drive. Very convenient note here. So for example, during the drive, note, fuel setting 1, 2, 3, 4, for example, just click that. Okay, so there's no need to type. You can type directly here, so here is fuel setting. Here's the note if you change gauges. Or some pre-fill note here for you. So and when you this is during the drive, so the note will disappear because it's new blow. But let's say if we have a pause, and here is a you select this blow here where you stop. You make a note there. No. Fixed hammer, for example. Okay, that note stay with that. So when you click that back, because you haven't moved the blow, so that note stay there. And when you view GPC review, the note the note summary is here. So every time you pause, resume, it automatically have that automatic note, or the time you change the fuel setting, that's when you click that button earlier. So that's the note in this table. Going back to, if you happen to change anything here, you need to save the file. So for example, this is a significant standby time. You want to run in GAPA, for example. You want to improve in GAPA. So change this to medium match, for example. Run the whole drive, all blows. So it will take a while. It'll take a while because I use medium match. But let's cancel. So doing this because it's, for example, the contractor is, hey, I'm ready. Let's go, for example. Then I need to click cancel. And because I did update the INGAPA from blow number 1 to blow around 24, because I did do that, I need to save. So I save it and I go back to the program, and because the contractor is ready. So for that, it did improve the INGAPA from 1 to 20, around 25, and from the 25 to the rest, it remained the same as before. So that NGAPA was the same as, it did not rerun NGAPA in my earlier few minutes ago. Let's see around this screen here. So in this, the box here is the case method. The box down here is the signal matching results. The graph, you have multiple graphs there. This is the stress graph. This is energy and stroke height. Beta, rebound per blow for top and toe. This is obviously rebound here is calculated based on the signal match results. And this is the envelope for the tensile stress. There's two envelopes for tensile stress. One based on the case method, one based on the signal match. So the black one is based on signal match. Remember that in case method is only based on 2L/C, whereas in signal match is the whole record. So the signal match tensile stress here will be more accurate than the case method because it's searched for the whole record, including the re-reflection from top down. So force travel to the toe, reflect back, and then hit the free end of the pie on top, and then cause another tensile stress going downward. So the signal match tensile stress is always more accurate than the case method. The case method is only 2L/C, and that's it. And it has compression stress envelope as well. So that is the cyan line here is the compression stress envelope, which other programs don't have. During nighttime, you might want to use the dark method. So it's different. It looks it maybe not. Maybe not. We need to improve this dark feature, the dark color mode though. But the dark is to use the screen in the dark. Light usually you use light. Okay, I think I cover everything in data acquisitions. Question, please. And then we go after the break. We go to GPC review will go again to NGAPA and INGAPA in GPC review. Any question?
Hard time seeing that from here, but are there two RNX volumes of that?
Yes, there are two. I turned off one of them, which is the unloading graph. So if you turn that on, it's in this case there's no unloading, so it's, let me turn off the NGAPA. So it's already it's exactly the same as the case method.
Oh, no. I just couldn't see it right. It's F and X.
Okay, yeah. Now over there is there's two numbers as well. The case method maximum and the unloading case method maximum. Okay. Same is here. So when the two are on top of each other like this, that means there's no unloading. Any online questions, Kelly? Okay.
I was just going to ask, as far as the hardware is concerned, I saw you were manually inputting the gauges. Those, I mean, given that it's the accelerometer and strain gauge, those calibrations are built into that gauge, or you're manually inputting those each time?
So future versions, it will auto-update like the 8G.
Smart gauge.
Right. But right now it's manually, we have to manually change. But the future version, it will ultimately detect what gauge. Regarding data qualities, this is similar to what you've seen in the PDA. The bending ratio, ideally, you want to be within 0.3 to 3, ideally. So F1 over F2 here. V1 over V2 typically very close to 1. When you have a gap in F, or last gap in F, you expect to see gap in V though, or smaller magnitude. So for example, if F1 over F2 equals 3, for example, V1 over V2 maybe around 1.05, 1.07. Velocity on the two sides of the pie are similar, despite the hammer force being applied unevenly. So the velocity are expected to be quite similar. At the end of the record, you want to see F close to 0 and V very, very close to 0. So that is indication of good quality. So during the drive, first of all, you want to see a smooth wave up from T0 to 2, from T0 to 2, and then you want to click on this and then go all the way to the end of the record to see if the V is close to 0, F close to 0. In this case, F is not 0 yet because the pi is still in motion. So for example, in this case, if you see this is soft drive, if you want to be very accurate, you might want to lengthen your post trigger length. So the post trigger length here is not long enough in this case. So during the ride, you see this, and you're very particular about this data set, then you can lengthen the post trigger length a little bit more. But obviously, this is a soft drive. It's not that critical in terms of capacity. So it's okay to stay with the post trigger length at this, even though it's not that accurate. But the soft drive, you only worry about tension stress, which is about, I would say about, it's not 2 LOC, but up to maybe 4 LOC. So this would be long enough. So when you see a small spike in the wave up, for example, in this case, a small spike in wave up here, can it be that the sensor was too loose in this example? or a different reason. In this particular example, the example here is monitor test pi number 4. You can open the example yourself. It is not actually because of the sensor being loose. It is because the sensor is a little bit too close to the hammer. And later on, when the pi is driven to the ground, there's no more room. Because the hammer lid is in the way, so they add a follower. And when they add a follower, let me go back. Let me open this that file. So when they add a follower, monitor test 4. Monitor test 4. Okay, so this is the point. This is the point before the follower. Small, really small spike, not that bad, but after that, it's extremely smooth because the sensor now are very, very far from the hammer impact because of the follower. The sensor is still on the pi. So when you see little spike on the wave up, it is because from the force or velocity. Reason number 1 is sensor might be loose. Reason number 2 is actually the sensor might be too close to the hammer. Here, F1 is very, very loose, and with a lot of spike like this, the data would not be usable. So this is bad data. I need to fix the situation right away. The loose sensor might be because of the angle itself, or might be because the ball was not tightening well. So when you see a lot of spike on the data, it's not acceptable. Now, force is not at the end of record when one is the pi is still, I forgot to mention here, one is the pi is still in motion. 2 is it actually pick up the signal of the rebound. For example, drop hammer, when we drop, the hammer will rebound back. So it will pick up the signal of the next pulse or of the rebound or the next blow. Or another scenario is the pi has a permanent change. So remember on slide number or the beginning here, it is the change is measured, not the force. So if you have a permanent change, that was interpreted as permanent force, even though force is gone, but that is because of permanent change. So permanent change here happen frequently to still pi. Still pi is being deformed at the top. So to minimize this, you want to put the sensor as far away from the pi top as possible to minimize the permanent change scenario. Another example here is on the centrifugal pi. As I mentioned, the centrifugal pi, the wall is pretty thin. Only in this example, only what is that? 7 inches, and the centrifugal pi actually have crack on the top. Because of that, has more frequently has crack on the top of the pi than our FDOT solid pi. FDOT is solid 18 inches, 24 inches, or 30 inches pi. You would almost never see crack on the top of the pi unless it's small, but it's small, the whole chunk fall off, not a crack. But on the centrifugal pi, you frequently you see crack, and if the crack happen to be through the sensor area, it will have permanent change, and this is what happened here. So this F2 sensor here is both loose and has a permanent change, loose because of the spike here. The monitor example here, it is 2D, but the pi is so small. In this example, the pi, this is a residential project. The pi is only 10 inches. So 10 inches, so even though it's 2D, it exceeds the standard. Standard call for only 1.5D. But even though it's 2D, so it met the spec, but because the pi is so small, the physical distance is too close. Any online questions? Okay, we have a long lunch break. 1 hour. Let's maybe we can resume here at 12:45. Thank you.
Okay, thank you, Ty. If there are no other questions, have an hour lunch, come back here at 12:45. We'll
Yep.
resume. Okay.
Thank you.
Okay, have 12:45 ready to start for our afternoon session there. So, Ty, that's all you have to do is click there and you're ready to go.
Thank you, Dr. Dick. Earlier during the, hello everyone, let's get back here. Earlier, I forgot to mention a couple of things. Now, the laptop is able to connect to the box using Wi-Fi, and I'm still able to present to you in Wi-Fi as well, because we have two Wi-Fi here. One Wi-Fi of the laptop and one external Wi-Fi. So I use this external Wi-Fi for the box, and I just plug in, I have another Wi-Fi. So I have two Wi-Fi here. And another option is I can use cable. I can use Ethernet cable. So the box has an Ethernet port here that I can plug in. So if I don't want to use Wi-Fi, and I can plug this Ethernet cable here to this port and plug to the laptop. So this cable is really, really cheap. You can buy it anywhere, eBay, Amazon, and you can buy as long as you want, 200 feet, 300 feet cable. So that's the option there for the cable use. For the 8-channel system, you can do 8-channel system. So let's get back to this. You can do 8-channel systems, which will require, right now, it's required 2 boxes. So one box with 4 channel, the other box with 4 channel. So you would have to have, in this case, 2 Wi-Fi to 2 boxes, for example, or one box using Wi-Fi, the other box using cable. In the future version, which Jordan Nelson is working on, we only have 1 box for 8 channels. So he will have, that will be, so as I mentioned, this is version 3. Version 4, 1 box would have 8 channels. So that's, so you don't have to use 2 boxes. So just 1 box, 8 channel. So that is acquisition. Now let's get back to the PowerPoint. Now we are here. As mentioned earlier, NGAPA is similar to CAPWAP. And this is from CAPWAP manual. The successful capacity of evaluation has little to do with blow count calculation. The capacity is closely related to how high the wave up rise up. So the wave up rise up within 3 hours, we see that is closely related to skin frictions, and the next 2 hours OC is closely related to the end bearing. So how high the wave up rise up is directly related to the high capacity. So blow count would change the capacity a little bit, not much though, with regard to blow count. So if you don't have to do driving criteria, you don't need to match blow count. But if you do driving criteria, then you do need to match blow count because when you match blow count, that is the conditions for the post-wave equations to do the analysis for the driving criteria. The model for signal match is exactly the same model for CAPWAP. So you here skin quake. The ultimate skin friction will be reached when the displacement reaches the skin quake value. And this is the skin quake unloading skin quake. In CAPWAP, QS unloading divided by QS is called the quake ratio, which is written as CS in CAPWAP. Now in NGAPA, let me close this, NGAPA, any example file here. Unloading quake is a standalone parameters, and in this table, if the users want to use variable quake and unloading quake for each segment, they can do so, or they can just keep it constant like this case. So that's quake and unloading quake, same thing for the tow quake and unloading tow quake. And so in CAPWAP, it's represented by the ratio. But here, tow will be the last row here. So the last row is the tow. So quake in this example, tow quake is 0.282 inches, and unloading quake is 0.189 inches for the tow unloading quake. I hope that it's readable from the online. The number a little bit small. That's the model, the static model. The dynamic model is related to the Smith damping factor. Smith damping is the unit is second per feet. So that is the model, and instant GAPA and GAPA is the have the exact same model. So when you just collect the data back, let me open a file that has not been processed. So I go to raw here, haven't processed. Let me pick this one here. And this one has not been processed, and the wave speed here has not been corrected yet. So the wave speed, top wave speed is different than the overall wave speed. So let's click on auto detect. Oh, auto detect wave speed. How come is no? Blow number one is earlier. It's not highlighted, but I changed blow number two. Auto detect wave speed. Are you okay with that? Yes. So let's run it, and it picked the wave speed now of 13,438, and it rerun through the whole drive. So right now it's rerun through the whole drive. This rerun is only for the case method. It has not rerun the NGAPA yet. So let's wait for a couple minutes here for it to run through the case method. This drive has 1,630 blows. So it will update the case method here, and I can let's run it through. I can I can cancel it. It will not update the rest, but later on, I can cancel that because I know that in the next step I need to rerun it again, so I can cancel that. Now, flow number 2 here, match quality is 6.96. This is because in the field, that's from the field. Earlier it did not match it, and if I click on manual GAPA now, it's totally different results though, because the wave speed has changed. So it here, and the match quality is actually worse than before because I just changed the wave speed. So let's run this. So when in GAPA, usually the default is not, this option is not checked. So you would want to check this in the manual GAPA. So you check that. What it does is it will look for the best damping option for the skin and for the toe. Now the auto procedure is either F3 or F4 or F5. That's the auto procedure. The most, let me click F4. The most third one is F4, and that's what I typically use, just F4. That's similar to auto CAPWAP. So it's done for this one, and you can keep trying to see if it's improving. Now there's a manual in the website. So if you go to the website, you go here, you go to the end, you can download the manual from this link, and you would have the manual. It will explain in detail what the options are. So I just did a manual NGAPA, and as I mentioned, I have a little bit of user influence here, just a little bit, but I can do more. This is a pretty good match already. This is soft dry observed blows, 6 blows per foot, almost no resistance yet. I can just leave it here, or I can manually keep changing more. So I can, for example, if I click the mouse here, I hit F6 on my keyboard, it will try to see if the program can improve just on the SS, which means SS here means damping for the skin. So it couldn't find anything better, so it left there. So sometimes when you select some number and you hit F6, I hit F6 now. You can hit F6 on the keyboard or on the screen here, and it may reduce the. I haven't changed anything, so this is optimized already. But you may see a little bit worse. Match quality though, a little bit worse. So if that's the case, then just go back to the previous analysis. So now let me go back to GPC, and because now it's resuming the analysis from before, but this resuming is just for the case method, not for the NGAPA. So blow number 2, I just did a manual NGAPA. Yeah. Now, when I click this and I click on subsequent blows, it will take a while. Click on subsequent blow. It will take much longer time for 1,630 blows. Each blow would take approximately 1 second. So the 1,600 seconds, that's pretty long. What's that divided by 60? That's is at almost 30 minutes. If so for this long drive, it will take almost maybe not 30 minutes, maybe quicker, but you can. So if you have time, just leave it there for it to run, go doing something else, and then come back half an hour for the in GAPA to run. So this is still in GAPA, but the office in GAPA, not the field in GAPA. So the office in GAPA here, it has been influenced by the second blows, which I just did. So it's instant signal match, but being influenced by the user analysis, which I did on the second blow. And now it will keep, each blow will keep improving based on the previous blow. Let's go back to PowerPoint while it's running now to see if there's anything. So right now, actually, I would need to stop. Right now, I'm still not matching the blow count. So let me let it run it for a little bit more. So for driving criteria, if driving criteria is needed, then I need to run NGAPA using a blow match level higher than zero. So right now it's still not matching blow count, purposely not matching blow count. So let me cancel this and let me show you. Let's select this blow, which is it's just did match grade 1.26, and let's see what it has. So 1.26. The DFN is, as I mentioned, the DFN is not this is super small in this case. The DFN is almost zero. That's why the offset blow by the program, you think that the offset blow is 3,000. So this is not the this from the LP. Blow count is not matched. So let me go back, and this is blow 347. And let me see on the LP table, blow 3. I'm sorry, you can see here both here. So the LP is 45. LP 45 here. So that the blow count based on the field record of GPC. Obviously, it depends on the user as well. If the user was able to keep track with the LP, it is for that foot. It is 44 blow per foot. Only 44 blow per foot from LP at 45 to 46. So when I change this to let me go above a few more blows and change this to blow match level 5 in GAPA subsequent blow, so it will reanalyze from where I selected blow 318 downward using match level 5. The higher the match level, the more effort the program try to match blow count. So, and in doing that though, it may sacrifice the match quality. So if it try to match blow count, it may sacrifice match quality. Let's see, let me stop here, see, wait, okay, so it go past that earlier. Which blow I was on? 300, I forgot now, 387? Let's go to 387, 387. So I believe earlier match quality was 1.25. Now it's a little bit worse. And when I click this, oh, how come it's still not, let's see. Maybe I have to do everything. Let me do this first then. This is going to driving criteria, so let me correct this LP first. Let let me show you how to correct LP. So I have a driving log here. I have driving log. Here is the driving logs of that pi. And on page number 2 here is the inspector blow count and stroke height FDOT form. So I copy this. I already did, but I am going to redo it for you for demonstration. But I already did here. But let me copy that to a new one here, and keep copying. Let me copy here instead, because I haven't copied the LP. The LP is formula, so if I copy and paste the LP, it will, let me do LP as well. The LP will not showing though. LP will show as error. But to fix it later on, because it's a formula. Let's do this here. Oh, actually, only to here, because only to 84.58. That's when the drive stopped for this pi, and then they remove template. They change the reference elevation, and so all the LP changed. So this first file is only to that. Why is it here? And unmerge all this. This is locale. This is stroke height. And you select everything. You do a filter. So I already add a filter. I already add a filter shortcut here. But if you want to find where it is here. Filter here, filter here. I already right click and I add that filter here, so because I frequently use filter. So you filter that, filter out the blank, so it's not showing the blank. Now, let me copy this to a new sheet. So I copy this to a new sheet. So in filter, when you filter and copy, it will get rid of all the blank rows, and then sum all the blows here. Do a sum of all the blows. So it has 1,693 blows, which is more than GPC. The reason is on the saximeters, whenever start and stop, if the inspector is not being careful, it will pick up noise. It will pick up noise on the saximeter. So there are, those blows are the junk blow, and I can tell that there may be junk blow here. Let me zoom up a little bit. I think there's junk blow somewhere here because the stroke is lower. Let me see on the record. It's still running, so I'm not able to see. But the stroke is much lower here. The stroke height. So whenever the saximeter has junk blow, the stroke height will be lower than actual. So it's same as up here on the first foot. That's when the hammer is starting, stopping, and the inspector may have a lot of junk blow there. So that's why it has more blows than actual. So let me do this. For example, the actual blows may be copied here to here, and let's say on the first foot only one blow, and they still have more blows. Let's now let me randomly reduce it somewhere so that I have about the same. I remove it in the beginning. Let's say in the beginning, so I still have how many more blows? I have 10 more blows to get rid of. So let's. I would think that when the hammer stop here, there may be some junk blow here as well. So let's put some here for now. So 4 more blow to get rid of. Let me see on the note. I don't know what LP is this. So stop to remove template, person change. So whenever that stop, there might be some junk blow. But anyway, let me just quickly change something here for now. 34. So now the blow count, the total blow count is matching. So let me go back here. Stop this analysis. So for the LP revision, so actually I have to do the sum first. So this sum of this and the cumulative sum. So this to the end here. That's the hold on. P2 no P2. What the heck? P2. Copy all the way down. So this is the cumulative number, which is the blow number. So I copy this to paste to this. So now the blow number is from that Excel. The last LP is 84.58. So I need to change this to 84.58 and then recalculate interval. Recalculate interval means recalculate this column number 3, which is the blow count per that interval. So recalculate interval. So now I have the blow count revised. So hit OK and redo this. So I have to redo this. Let me hit all blows. So what all blows mean? All blows means it will redo each blow using the existing results of that blow. So earlier in GAPA, the result is stored there, and it will reuse that to improve it. So let me. One of the I have to say one of the weakness of this program is it can be open only one time. It cannot be open multiple times. So even if you call the program, if you call the program, it's not going to open multiple times. It's only one version here. So if I call the program, oh, I don't have it here. I thought I have it on my desktop, but it will not be called the second time. So if I want to open another version, I have to use the program. So I'm going to use the program to open the analyze file. So I have another analyze files already. So let me open that while the program still calculating. The other program still calculating in the background there. So here, for 4L Pi 5. Oh, I did. And then let me see if this latest file. The date is September 4. Let me see if I have the same. Yep, it's there. So this is the one that I already reanalyzed. So this one has been reanalyzed with blow count matching of 5, with medium match. So let's go to blow 387, and when you click that, the blow count here has the record has been adjusted to 35 blow per foot, which go back, which is this time is not, the LP is not 45 to 46 anymore. It is from 46 to 47. So let's see here, blow 387. 387 is 46 to 47. So 46 to 47, 35 blows per foot. And because it was a blow count match level higher than 0, the record has been adjusted. The program already adjusts for you, so that it's 35 blow per foot on the record. Now I'm going back. If I change match level to 0, going to change match level to 0, and if I click this, that means it's no adjustment. So I click this, it's no adjustment. That's the raw data. That's the raw data without any adjustment, which I showed earlier. That the DFN is not necessarily accurate because of the double integration. So with any blow level higher than 0, it will adjust the record so that the blow count is matching with the observed blow count. Now in the futures, as I mentioned, we will use the LP sensor. So with LP sensor, each blow may have a different blow count, not necessarily the average of that foot, because even though it's not every blow for that foot will behave the same. So right now we use the average of that foot. Okay, let's go back here. Let's go to PowerPoint to see. Okay, we are on driving criteria. So we are close to end of this presentation already. So on one program is still running. On this program is still running. On this, let's do driving criteria. So the required bearing resistance here is 634 kPa. So with this, first of all, you want to print the report. So you print the report out. Let me do some filters so it get rid of the some of the zigzag there first. So whatever you see on the screen, it will be the same format as report. So if you view per blow like this, the PDF will be per blow. But if you print per LP, so this is per LP. You click that per LP, the left side is LP in feet, and the right side is the elevation, the pie tip elevation. Now, I forgot to mention that some of the graph, because of the space not enough, we only show the legend when the mouse is hovering on the graph. So only when the mouse is hovering on the graph, then the legend would show. So right now I'm showing the per LP. I print the report, print PDF. Let me put it out to document here. Example. So I have this report where it shows exactly what, as you see, on the left is LP, on this right here is pi toe. Here, let's see, the NBR is 634, so this is the foot, the 80, this is the foot here, let me highlight it, this is the foot that just exceed the LBR, and we have a few more feet here. So I want to do a driving criteria on this foot, the NGAPA, average NGAPA for that foot is 784. Stroke height average is 7.23. So, and this is for LP from 81 to 82. Okay, so let me go back here. And 81 to 82, is with the blow number from 1,390 to 1,448. So it is this. No, I'm sorry. To LP 82, I'm sorry, 81 to 82. So LP 81 to 82 is this, I'm sorry. With blow count of 58 blows per foot. So 1390, 1448. That's the range of blow that I want to focus on. So I click on blow list. I forgot now. 1390. 1390. 1448, I think. 1448. So I select that range and copy to clipboard. That's the foot that I want to do the driving criteria on, which is this foot here, 81 to 82, where the capacity does exceed the NBR. So copy to clipboard, go to Excel. A new sheet here. Paste to Excel, and this is comma separated. So we need to go to data, text to column, then delimited, comma, finish. So that's the range that you have for that foot. Let me do the filter again, and I'm going to sort this by the stroke height. So I'm going to sort this by stroke height, and as I mentioned earlier, for that for the average, the stroke height is 7.23. So I want to see what I have around that. So around that, I don't have any blow with that exact stroke height, but this is about that. Let me freeze this. View, freeze this so you don't show my heading. Now, if I choose a blow with a higher stroke height, so this is tend to be higher stroke height, that means my future driving criteria would be a little bit more conservative, because I use the higher stroke height to represent the average. So my driving criteria would be a little bit conservative if I choose a higher stroke height. But at the same time, though, it depends on the capacity as well. But if the capacity here is also higher, though, the capacity here also higher than the average. The average is 784 on the NGAPA and 728 on the case method. So the capacity here is higher as well. Case method is here. So I can choose any blows, any blows here. Let's see which blow you want. Which blow you want? Mingo, which blow you want? Whichever blow you want. I'm sorry, 1425, 1425. Okay, so so below 1425, let me go back here. So 1425 is this blow here. The stroke is pretty close to the average. Case method is pretty close to average as well. So let me select this. So when I do this here, when I hit OK, it will jump to that blow. Hit OK, it will jump to that blow, and let me do manual NGAPA to see what I have here. So it has been, the record has been adjusted to meet the observed blow count. So the observed blow count is 58, so it has been adjusted already. Now the match is not quite good yet. Let's see if I blow count here. If you have an observed blow count higher than the observed, that would mean that your future driving criteria is going to be a little bit more conservative as well. Let's stay with blow count match level 5 for now to see what happened in F4. Okay, so the blow count increased a little bit. The capacity reduced though. Capacity reduced, which means it's toward conservative one. Let me go see the previous. So previous match quality is 2.25. Capacity is over predicted. Capacity over predicted. The current one capacity is lower. Let me change this to be more aggressive to see what happens. More aggressive. When I change this, it will try to be more aggressive to match the blow count. And hit F4 again. So let's see, F4 again. So right now with the automatic one here being influenced by a match blow count level of 10, I still have a little bit higher blow count. Again, when you have a little bit higher blow count compared to the observed, that means your future driving criteria will be a little bit more conservative. The capacity here is under predicted here because the calculated is lower than the measure in terms of the maximum wave up rise here. So the red one is lower than the blue one. It means this is a conservative number. So everything here kind of conservative. You can manually change this. For example, if you think that the skin friction based on the soil boring or whatever, you think that the skin friction is would be more spread out, you will reduce that. You hit F6 on the other box to see if it can, F6 here, it try to, because I reduced the lower one, now it try to have 68 capes on the upper one. Let me purposely change that to 50 as well, and then hit F6 on the upper one. It's assigned 18 here. Blow count is further out. If I increase the toe, bearing, this one the predicted capacity will be higher. So let me make it 550, for example. 550. Oh, by the way, in NGAPA, when you change any number, the result will be reflected right away. You don't need to do anything. So when I hit enter, it will change the results immediately. You don't need to hit F2. So whatever you do, the results will be reflected immediately. So when I increase the toe, the capacity is more closely matched, but blow count is further away. So that's the reason when you do automatic match, try to match blow count, the in this example, the match quality may be sacrificed. So so let me hit F6 on this toe, see what it has. So if I hit F6, it thinks that the end bearing, the best end bearing for this here would be 600 kip. Total resistance now match at the toe. The skin friction is not quite matching yet though. The skin friction here is higher. Change this to 10, for example. 10, oops, that's too much. Let me hit F6 here. Okay. So when you change, as I mentioned, when you change here, it will change the result immediately. Let's let me. It's so for this, if I use this, my driving criteria would be very conservative, because my driving criteria would match with the 78, which is very conservative. It's up to you what level of conservative you want. If you don't like this, use the automatic one and try and it will sacrifice the match quality though. Or in this example. So this looks okay. Match quality obviously not 1.62 as before. Now is 2.343. Blow count pretty close. It's kind of matching because all the parameters change. Let me see what the significant change. Significant change is the toe quake. So if you go back and forth here, you can see that the toe quake is the one that changed the most. So let's assume that we use this. So we use this. For this, when you have this and you did not want to save any extra bookmark, during the process, you can add your user bookmark. You can click here and you add user bookmark, but I have not added any user bookmark. So I don't even need to save this NGAPA file. I can click here to save, and I save this as a separate NGAPA file, but I don't need to. I can just let this to be included in the GPC file. GPC file is the TDMS file. So this is blow 1425. Let me see. So I can only save this TDMS without the need to save NGAPA. So I save this TDMS file and close this. Oh, this is the program. Let's see if it finished running over there. Oh, it did. Yeah, it did finish running over there. So let me talk about this a little bit. So here, at the end of the record, though, there are few blows that I need to turn off. So let me go to the end of the record here. So here is the dead blow. It has no signal, so I need to turn it off. I don't need to include this in the summary. Let's see. So where in the graph here, there you see the spike there. So let's go up one more. Let's see where here. So in one of the blows, in one of the blow, when the contractor is turning the hammer off, for some reasons, maybe the hammer lead caught the cable. It has a spike in F1, which spike doesn't have in other blows. So this blow doesn't have, all the other blow doesn't have, only one blow here. It has the spike. I believe that I was not on the job site on this part, but I believe that when the contractor is turning the diesel hammer off, when they pull the rope, for some reason when they turn it off, everything was shaking, the hammer lead was shaking, and it may caught the cable on the sensor and cause the spike. So this record is not to be used. So I would turn this off as well. So I turn this off and it will not have that spike at the end there. So, and the subsequent blows are the dead blow as well. So this one, the stroke height is only 4 here, down here. Stroke height is 4, I'm going to turn it off. This one, the stroke height is not detectable, off. And yeah, so those are the dead blow at the end there. So I turn off the few blows at the end there because one blow was bad and the other blow are the dead blow. So that's the analysis is done for this, and I don't want to save this file though. So but basically I just finished analyzing using a blow match level 5, which I just revised the LP based on the driving log from Excel. Now, case method are not necessarily the same as NGAPA, which means that along the depth here, the case damping is not a constant. So from here to here, the damping is 0.6 because it is the same. But from here, for example, from here to here, the case method is higher, which means that the case method is over predicted, which means that the damping is too low for this portion. So in this portion, damping may be, for example, 0.7. In this portion, case method is under predicted, which means that the damping is actually high for this portion, which means that the lump case damping in this portion may be, for example, 0.4. So for the whole length, again, case method is just a rough estimate. That's not the gold standard. You can use that as a rough reference, and along that, the lump case damping is not a constant. So again, I don't want to save this because in this folder I want to keep it as raw Haven process for my future presentation. So I don't need to save this. So close. I want to close this file without saving. Yes. So close. And I did save the other file though. So when I did this, I did save the other file, which blow 1425. So now let me open GPC wave and import GPC blow TDMS. So import, and that file is this file, which is I just saved 10 minutes ago here. So open that file and blow 1245 on 1425. So when I click that, the stroke height from the file is 7.25. Now, if this is a hydraulic or air hammer, there would be no stroke height, and the user would need to enter here. So at the time, this box will be visible for the user to enter the stroke height for hydraulic and air hammer. So hit OK. So this is, let me put it here. So this would be wave equation signal match. So this one is directly imported from the signal match, and see this transfer energy here. The transfer energy is 36%, which is by calculated. So let me go back to the slide and the PDF as well. So in the PDF here, you have the transfer energy printed out. For diesel hammer, around 30% is very common for a diesel hammer, around 30% transfer energy. And back to the slide. In 2006, also the same, exactly the same as the previous version of the driven pi manual. This graph is showing the transfer energy for different hammer on different pi type. Concrete or timber, the mean is 26%, only around 26%. On steel, it's higher. The reason on steel is higher because there's no cushion. There's no pi cushion. So it's higher transfer energy. And so on and so forth here. So here we have this wave equation signal map. And now it's very simple for the driving criteria. So driving criteria, you shoot for 634 kPa. So you change that 634 kPa. And you can hit F11 now. I have not done that, but you can hit F11 now. It will have a set of driving criteria for that 634 kPa. Now, remember that production pi, the pi length may be different. So you have to change the pi length. So change the pi length here. It's really simple. Whatever you earlier recommended. Let's say you recommended longer pi, 100 feet pi, for example. So you change to 100 here. So change that here. And if you want to be even more conservative. So this driving criteria, to start with, it is already a little bit more conservative because the match was for 61 blow per foot, whereas the observed is 58. So to start with, is already three blows more conservative already. But if you want to be even more conservative, you reduce the transfer energy, which obviously you guys have done all the time when you do whip. You reduce the efficiency of the hammer. The reason is during the production pi, you don't know if the pi is the same maintenance status as a test pi. The efficiency may be lower. So if you want to reduce that one, so let me reduce it to less, for example, 33%. And now, after I'm done on that, I hit F11. So for 7.25 foot strokes, it requires 57 blows to have this capacity. It refresh it to have the table here, and that's the table. That's the tables that goes with the driving criteria letter. So if you want to change the increments, you change it here, 0.3 for example, and then it tabulate for 0.3 increment. So that is the stroke height and blow count here for driving criteria. So this process is targeted for driving criteria. As such, is very simple, much easier than whip. Whip, you have to do not a lot of manipulation in terms of pi cushion, in terms of efficiency. So when you guys done that before, you have to juggle a lot to be able to match with the CAPWAP. And then after that, you produce the driving criteria. But here, such importing process is extremely simple, and that's done. And you put a note here. So this is blow number 2 on my file here. So I put a note here that is driving criteria. So when you print this out, so the print results here. Print results, example, download, document. So driving criteria. So you have this, just one page. It has the table and the note that you put in the front is the driving criteria. I have a typo, but that's the driving criteria table. And when you go back to blow number one, you go back to blow number one. Oh, I just did something. Did I change anything? No. So we're going to go back to blow one, which is the wave equation signal match. Hit refresh to refresh this table. If you want to print this table, signal match, you don't need to show this table. This is the signal match. It matches the N-GAPA part there. So you print this, and that would be wave equation match. So that would be the 2 pages for your driving criteria data. One page is the signal match page, and one page is the driving criteria match. Let me go back to the program. I forgot to mention one thing. When you do the wave equation, the GPC wave, the file automatically saved. It's always automatically saved for the acquisition as well as GPC wave, and the location is here. So if you want to see where the file is, it's here. Let me close this and go back to GPC review. GPC review. Now, when you print report, the default option is that it will not print the rebound column. So there's a couple of columns that has the predicted rebound. So the default is not print the rebound, and it will print the energy transfer. So that's what I did earlier. So this is what I did earlier. When it not print the rebound, it will print the energy transfer. When you check, is it now? Where is it now? Oh, yeah. So when you check this button, it will print the rebound columns in the report, and because of this space limited, it will not print the energy transfer in that case. So print here, document example 2. So if I print this, it will print the top rebound and toe rebound prediction without printing the energy transfer. Let me see if I cover everything. Yes, yes, I cover everything. The last part is for whoever interested. Is pipe preparation. Most of people either already knows or not necessarily interested in this. But before going to that, any questions online as well as in person here? Let me see. Where do I see it? Here.
Okay. Hey, Ty, this is one. You got a question regarding this energy transfer deal. So when you're doing the NGAPA, are you somehow is the NGAPA program?
Hold on. Let me turn off my volume here. It's echoing.
Yeah.
Turn off volume here. When I run NGAPA.
Okay. Yeah, I mean, I noticed that the results you end up with energy transfer. You can play with the energy transfer to come out with the driving criteria later on. So that means that in the process of NGAPA, you input the hammer, and then you come out with the
yes.
With
So
the energy transfer.
Yes.
Okay.
So in the GPC, the hammer is already known here. So hammer known. So the ram weight is known, and the stroke height would be known from. I haven't closed one of these screen. I haven't closed one of the. Oh, here. So the stroke height is known from whatever selected blows, 1, 4, 2, 5. Stroke height is known, hammer is known, ram weight is known. So yes, so because of that, the transfer energy is known from the record.
But what about the NGAPA?
The NGAPA directly, the NGAPA directly take the information from here. So if you run NGAPA from other sources, so let me open NGAPA from other sources. So when I have NGAPA from PDA 5, for example, not from GPC. So when I have NGAPA from other sources, I have to enter hammer. So hammer is needed for GPC wave post test. So if the NGAPA is from GPC, this button will disappear because the hammer information is saved with the file. So in this case, I have to hit this button and enter the hammer information here. So when I enter hammer information here, then it will be part of the NGAPA file.
Got it. Okay. Thank you.
Yep. Thank you.
Video on YouTube for the driving criteria development process. Is that one of those you have posted on the web?
I posted the NGAPA part. The driving that I had never presented before. This is my first time presented the driving criteria. Earlier is all NGAPA on all different pi, on pi with splices and on stinger pi. Those are NGAPA. Okay, if you have, if anyone have question, you can always send me email. Let's go to the last portion, which as I mentioned, a lot of you already know. I have a YouTube video here, which because it's not quite presentable or marketable or thing like that. I put it private though, but anyone can click on the link. And this is on steel pi. So drilling, if you have a pilot hole, it would be best. And then I would recommend not use this though. In this video, we use an auto tap. The auto tap, I eventually find out is not. It saves a little bit of time, but it's not the best. You should use manual tap. So the auto tap here is pretty quick, but it's not always the best. On steel pi, because of vibrations, you want to use a lock washer along with flat washer. And the later portions, I have how to prepare the concrete pi, which I use this tool, which is very convenient. I didn't know about this this tool until only years ago. So this tool has a tip and a punch within it. So use this punch with the drill, with the drill in hammer mode. Is very fast and reliable. It's very much more reliable than use the handheld hammer to punch the anchor. I use this in this video as well. Use that tool to blow out the dirt and put the anchor in, and then just punch using that drill with that attachment there. So it's very convenient, fast, and reliable for concrete. So the distance here, the standard is 1.5 D. The further down, the better. In this case, the example here, the guy who was drilling the pie make it parallel to the ground, which is bad because the pie was not parallel to the ground. The pie is on the truck, on the bed, and the hole end up not parallel to the pie. And this is not a good situation. The force and the force as well as the accelerometer's results will be smaller. For pie, if it's really large, you want to use 8-channel system, or if it's spiral welded, you also want to use 8-channel system. So you would drill or four-side the pie and avoid the spiral weld. Yeah, that's about it. And for timber pie, with obviously the input, the help from Dr. Mingo came here, I found out that for timber pie, even though it's small pie, 8-channel is needed. When I did the timber pie, with just 4-channel, I said, wow, what is this? The data is all messed up. I called Mingo. He said, hey, try 8-channel. So I tried 8-channel and the result is perfect. So so with the timber pie, even though the diameter is really small, only 10, 12, or 14 inches, sometimes you need to use 8-channel because of the way the force is propagating not uniformly through the grain of the pie. So that's about it on the prep, on the pie prep. And again, if you have any questions, you can always call or email me. All right. Let's see if there are any questions.
That was going to be the question. I'm sure folks are going to ask as far as where to get the references there. Probably updated on the website there. So, and I think the presentation was sent out to all the presenters, the districts there. You don't have a problem with them forwarding out to the other participants. Okay.
No problem.
Okay. So, okay. Okay. Last chance. Any questions there before we wrap it up? Nope. Okay. Okay. That's it.
Right.
Thank you very much, Ty.
Thank you so much.
And thank you everybody for attending there. As Ty mentioned, if you do have questions afterwards or reviewing it, have his email address there, and more than happy to answer any questions.
Yeah.
Thank you, everybody. Have a great afternoon. Take care.
Thank you. And